Howdy, we are the Laser Weed Management System team, partnering with AgriLife Research, consisting of Karthik, Nadir, Jacob, and Andrew. Agricultural weed growth is both a financial and labor-intensive problem in our current modern-day society. Current methods are either tedious and/or chemically damaging. Our team has provided a solution to promote organic farming and optimize costs in the farming process, using high-powered lasers and image processing. Within our project, we consist of four separate subsystems: image processing, power supply, hardware motor control, and data collection.
For the image processing, we utilize the NVIDIA Jetson Nano, featuring a 128-core Maxwell GPU, along with a Pi Camera V2. The program was written in C++ with OpenCV as the main library. The images were downsized, thresholded, filtered, and then contour detection was applied in order to detect target objects in the image. Thanks to the GPU accelerated processing unit, the image processing runs at a steady 13.5 frames per second, allowing for real-time detection of weed centroids.
The hardware and motor control subsystem is mainly focused on the creation of a two-stepper motor gimbal system, which is used to accurately target the centroid of a weed. To complete this process, the NVIDIA Jetson sends control signals to a current amplifying MOSFET driver board, whose output goes to the stepper motor control boxes. The motor movement is calculated from the image processing system's centroid coordinates. Using the XY coordinate of the centroid and the height of the motor, trigonometry is used to calculate the angles, which can be converted to steps for the motors. The system is generally functional, but we're currently working on refining the movements to be more accurate. By time we demo, I expect the system to be able to accurately target the centroid of a weed, maintain aim for a predetermined amount of time, and then return to its home position.
The laser research and analysis scope of this project was heavily aligned with coordinating with our AgriLife sponsor to determine the most efficient route of weed termination. Multiple plant trials were held and simulated to real-world conditions in order to identify the optimal method of killing the broadleaf species weeds, whether this was at the centroid or the base stem of the plant. Correlation points were also found in order to help identify the respective death rate percentage for a specific laser application time. This data would be used for the future observations in ongoing research project.
The power supply subsystem consists of three buck boost converters that will convert a 12-volt input from an external tractor battery to 5 volts, 12 volts, and 24 volts to power the microcontroller, the lasers, and the motors, respectively. The 5-volt, 12-volt, and 24-volt buck boost converter PCBs were designed using Eagle. Each buck boost converter PCB was tested and verified and successfully output a specific voltage at the needed output current of the device it's powering.
This is a quick demonstration of our system. Here we're using a potted plant to simulate a target object that has some height. Thanks to Karthik's research, we know the best place to target is the base of the stem, so we designed this demonstration to target the pot that the plant is in. While there is still a lot of refinement that future teams can do with the camera calibration, we were happy with our overall accuracy this semester.
A special thanks to our AgriLife sponsors and our Capstone professors.